So we had a question about this one, which is 29.56a. It's from the practice homework. And you've got a coaxial cable where there's a really thin shell of current. It's yellow. I called it yellow here. And then a little wire inside that's sort of got current in it. And the currents are in different directions. So let's just label the currents. Let's say this is I1 and say that this one maybe is into the page or in opposite directions, and say that the current over here is I2 coming out of the page. And there's two radiuses. So there's this radius R1 here, and that's really hard to see, and then the radius R2 over here. So maybe if we use a different color, that might help with that. And you're told to try to find, it doesn't help either. But R1 is the inner radius of that guy over there. Let's try this color. Maybe this color works. There we go. And you're told to try to find, in the first case, you want to try to find the magnetic field for R that is less than R1. So you're like inside here. And so I'm going to make a little Amperian loop here inside this piece. And I'm going to call the radius for that guy to be R. Okay, so R1 is the total, this little guy inside here, and R is this one over here. And I think in this problem they actually say that the currents are equal. So we'll just make them both I, just that one's in and one's out. And so this is a Ampere's law problem. So we write this kind of business here. So the B dot ds, and again, so we've got cylindrical symmetry here. So this works out to be B times 2 pi r. So the B field is parallel or tangent to this Amperian loop for the whole over it, and since it's the same distance away from the center of the cylinder, it's constant. And so we can write it out like this. So absolute value of B times 2 pi r equals mu naught. Now here's where the tricky part comes in, I enclosed. And so I enclosed means that we want to somehow figure out just the current that's enclosed by our loop and not the total current. So you want yes, so again we want the total current inside the loop, so some sort of percentage of our current here. And so the way to do that is to use the cross-sectional area. And so what I'm going to do is say pi r squared divided by pi r1 squared. So let's think about this. If our Amperian loop has a radius of 0, this gives me 0 current. That makes sense. If my Amperian loop actually has the radius of r1, this would cancel and I get the full I. So this seems to have the right sort of functionality that we want. So I'll put pi r squared pi r1 squared, and now basically we're done. So we just do some algebra, cancel out those pi's. Over here I'll solve for b as a function of r, and I get mu naught. Oh, and I forgot the I over here. My bad, sorry. I, and then now this r will cancel the 2 over there, the squared, so I just get r by itself. And then downstairs here I get 2 pi r1 squared. And so that would be, again, the magnetic field inside that radius r1. All right, hope this helps. Thanks.